Our last section in chapter 16 is on Lewis acids and Lewis bases. Sometimes I've seen the terminology have, pair, will, share used with Lewis acids and bases. That means that if you have a substance that has an extra pair of electrons hanging out on it, it'll sometimes share those electrons, and as a result it becomes a Lewis base, and the object it's sharing with becomes the Lewis acid. So your Lewis acid is your electron pair acceptor, your Lewis base is your electron pair donor. So compounds with nitrogen tend to be pretty common Lewis base because of that lone pair right there. Can share with atoms like boron to form an ion like this. And so this would be our Lewis base because it's our electron pair donor. This is our acid because it's the acceptor. The hydrolysis of metal ions to form complex ions, which we saw in the last section, is actually another example of this. The unshared pairs in water become attracted to that metal cation, and as a result you end up with a Lewis acid and a Lewis base, where water is your Lewis base and the metal ion is your Lewis acid. So let's run through this last example problem, and this covers not just stuff from this section, but stuff from several sections in this chapter. First, we're going to see why is H3PO4 diprotic and not triprotic. And to do that, we're going to draw the Lewis structure of phosphorus acid. So here's our Lewis structure for phosphorus acid, and if we notice, there are only two hydrogens that are attached to oxygens, and remember oxygens are very electronegative, and so that means that we have two hydrogens that have very, very polar bonds between the oxygen and the hydrogen. These are your acidic hydrogens. These are the hydrogens that can be easily removed from the anion. This hydrogen here is not acidic because it is not attached to a very electronegative ion, so it is not easy to remove that hydrogen. So this makes this acid diprotic instead of triprotic. Part B of our question says we have a 25 milliliter sample of the phosphorus acid. We're titrating it with sodium hydroxide, and it tells us it requires 23.3 milliliters of NaOH. What's the molarity? So here's a good old titration problem. This is a real old review. So we know when we're doing titration problems, we always start with our balanced chemical formulas. So let's go ahead and start with that. Notice that my anion here is HPO3, not just PO3. And it says in the problem we have 25 milliliters of this solution. It says the molarity of the NaOH is 0.102 molar, and that it requires 23.3 milliliters. So since I have volume and molarity, I can find moles. Since I have my mole ratio here, I can go ahead and find the moles of H3PO4, and then once I got moles of H3PO4, I can find molarity of H3PO4. So I'm going to go ahead and do that. So here's my moles of NaOH. Now I'm going to use my mole ratio to find moles of H3PO3. Now that I've got moles of H3PO3, I can go ahead and I can find molarity of H3PO3 because I have volume. Our molarity ends up being 0.0475. Okay, so let's take a look at the next part of the question. So it tells us the pH of the solution, and it wants us to find the percent ionization in Ka1 for H3PO3. We're assuming Ka1 is much, much larger than Ka2. So if it gives us pH, we should be able to find hydrogen concentration because we know our magic little pH equation. So this is 0.026 molar solution of hydrogen ions, and it wants the percent dissociation. Now one thing that students will get confused on is they'll take a look back at this equation they wrote back here and try to figure out where those hydrogen ions are. Well, the hydrogen ions aren't coming from this reaction, they're coming from the dissociation of the weak acid. And so we have a new equation now. We have the reaction, the equation of just the weak acid dissociating. And so this is going to be our equilibrium equation that produces hydrogen ions. So this is the equation we want to deal with. And we have the equilibrium concentration of hydrogen ions. So to find the percent dissociation, we can set up an ICE table to do this. We just found the concentration of H3PO3 up above to be 0.0475, and we know the equilibrium concentration of hydrogen ions to be 0.026. So with these two numbers, we can go ahead and finish filling in our ICE table. It means this is also going to be 0.026. These started out at 0, which means they changed to 0.026, 0.026. This went down by 0.026. Which makes this 0.022. Actually, I don't really have to go through and finish the entire ICE table to do most of this, because really the only numbers I needed were that number and that number. I don't even have to figure out the rest of it, but it doesn't hurt to go ahead and do it. So I have the original amount, 0.0475. I have the amount it dissociated by, 0.026. So I just find the percent dissociation, multiply it by 100, and I get about 55% dissociated. Now to find the value of Ka1, I will need the rest of these values. So now that I have my three equilibrium values, I can plug these into an equilibrium expression, and I'll get my value for Ka. And I get a Ka value of about 0.030. And both these values, the high percent dissociation and the relatively high value of Ka, indicates this might be a weak acid that is actually a fairly strong weak acid. Now the last bit of our question asks, how does the osmotic pressure of a 0.05 molar solution of HCl compare with that of a 0.05 molar solution of H3PO3? Now remember from a few chapters ago, osmotic pressure is a colligative property, which means it depends on the amount of the substance that is created, not what the substance is. So if you have a 0.05 molar solution of HCl, HCl has complete dissociation into 2 particles per every 1 particle of HCl you put in there. So a 0.05 molar solution of HCl will produce 0.1 molar amount of particles, H positives and Cl negatives. For H3PO3, it's not going to produce nearly as much, as many particles, even though it dissociates into 3 ions, 2 hydrogen ions and 1 HPO43 ion. It doesn't dissociate nearly as much. It ionizes to a much lesser extent. And therefore, it's going to have a lower osmotic pressure because it doesn't form nearly as many ions as the HCl does.